Okay, so hi everyone. Welcome to your third practicum. So because we adapt to this new setting where we try to release the practicum 1 week in advance, I hope you have some time to look at the practicum already. So I would proceed to just go through the practicum and then discuss the solution with you. Is there any objection? Does any one of you wants like 15 minutes to look into it yourself first, or? Okay, if not, then I'll just get right to it. So this practicum is on meta-learning. And as you have learned during the lectures, meta-learning is learning how to learn, like how do we train a base model so that in the future, when you need to fine-tune it with a very few amount of samples, that it just quickly adapt to the new task. So in this notebook, we discussed 3 popular meta-learning algorithms. So we have prototypical networks, model-agnostic meta-learning, or we called MAML for short, or proto-MAML. So we discuss all of them in theory, but then we only focus on the implementation of proto-MAML because it's kind of like the integration of them all. So the task is this time is few-shot classification, where the training and test set have distinct sets of classes. So for example, during training time, you would have binary classification of cats and birds and fowl and bikes. But then during test time, you need the model to be able to distinguish between dog and others, given only 4 examples of each class. So as you can see here, the task given to you during the training time and the test time is different. However, they're just similar in the type, but not exactly in the training data. So here are some examples. I guess it's quite demonstrative from what I mentioned just now. So the first part of the code, you just import the standard libraries with PyTorch, PyTorch Lightning, and then some library to process images. So this part you can just take for granted. Here we also define some paths to store our data and models, and also set the seed so that you can reproduce everything. Set the device so that you can make use of the free Colab GPU, but then you can also just use CPU if you're out of quota. So because the training of the models in this notebook is quite long, it takes between 2 to 8 hours. And the evaluation algorithm is also taking long because you have to do fine tuning on a few samples every time. So we download the pre-trained models and results so that we can just directly look at it. So this notebook is just like for demonstration how things would be working. So yeah, this code you can also take in for granted where you just download, install the files. Now we go to the implementation of the task. So we would use the CIFAR 100 dataset with 100 classes each, with 600 images of size 30 by 30 pixel. So usually for a normal classification task, you would split the training, validation, and test set like sample based across the whole dataset. But because here we're doing meta learning, so we want to simulate the scenario where you have not seen the classes during inference during training time. So here, instead of splitting just by sample, we would be splitting by class. So because we have 100 classes, we will use 80 of them for training, 10 for validation, and 10 for testing. Yeah, and our overall goal is to obtain a model that can distinguish between the 10 classes during test time with only very few amount of samples of those classes provided to it during test time. And below here is some code for you to just load the test set and then load the data set and then have a look at what kind of pictures are there, which you can take for granted. So the next step is to do data preprocessing. So because here we load the data set using the Torch Vision packages, and they would provide the training and test set split in the normal way, as I mentioned before. So what we would do is that we merge all of those splits together, and then we resplit again according to the classes. So here's the code for merging. To have an easier time handling the dataset, we define our own dataset class as below, where we take a set of images, labels, and targets, some potential image transformation, and then returns the corresponding images and labels element-wise. So I guess here is your first to do, if I'm correct. Yeah. So your first task here is to implement this get item from the image data set class, where you're supposed to select the image and the labels given the index. And you're supposed to convert the image from the NumPy array to the image object from the PIL library, and then apply to any potential transformation if there's any. So here's the code. So you just select the image and the target from the array, so from the set of images and targets from the data, select by the index, and then you transfer it to the image object. And then if there is any transformation required, then you apply those transformation. So yes, that's it for the first item. And after that, we can create the class list. So as mentioned before, we will assign the class, we would split the train, validation, and test set based on the classes with this ratio. So this is the way we implement our solution, but of course you're free to do any other variants. So here I just do a random permutation of numbers from 0 to 99. And then assign those already permuted indices to the train, validation, and test set with the given predefined portion. And then there's some code for you to print out the names of some of the classes in the data set. And your next task is to create a function where you take the list of classes and then return a data set that corresponds to the split. So this is your next task. Here you just within the targets you select. Okay, so as the input here you have the list of images, list of targets, and the subset of the classes that belongs to the split that you want. And then the first thing to do here is to select out of the targets which classes belong to the subset of classes that you want to belong to the split. And then you return the image dataset, which you have defined above, just filtered by those selected classes. Afterward, we normalize the dataset. So, and additionally, we would use a small augmentation during training to prevent overfitting. So the data means and the data standard deviation is already pre-compute. So here you can just plug it in directly, but you can also just recompute them if you want. And here you do some transformation, normalizing, and then some augmentation with resizing, cropping, or flipping. And then afterward, you can finally define your train, validation, and test set. So yes, so that's for data pre-processing, I hope. Is there any question so far? Okay. Next, we will get to data sampling. So the idea of meta learning is to simulate few shot learning during training. So at each training step, we would try to randomly select a small number of classes and then a small number of examples for each class so that you can simulate exactly what happened during test time, that you have these new classes and only a few samples for them. And we will refer to this as support set. Additionally, we sample a second set of examples from the same classes and refer to this batch as query set. And our training objective is to classify the query set correctly from seeing the support set and its corresponding labels. So the support set here acts as the fine-tuning data during testing, and then the query set is like those hidden label that you want to predict correctly. So it's kind of like validation-ish set. So the main difference between the three methods that I mentioned before for meta-learning is that is in how they use the support set to to adapt to the training classes. And here in this code, we have a class that creates such training batches. In PyTorch, we can specify the sampling procedure by a sampler, and samplers are simply iterable objects that return the indices in the order in which the data element should be sampled. So because we want a quite special setting here, where each batch of us have like a few classes and then a few examples from each classes. So we would have to define a sampler by ourselves. And here you would have your next to-do item, in which you should sample the classes and the example from the training data. So here we already defined n-way, which is the number of classes, and k-short, which is the number of examples per class, whether to shuffle it or not. Yes, and here k-short is multiplied by 2, which I will explain later. Yes, and then given that, you can already select, so given a list of class, so the way you split this into multiple batches is that you keep taking a set of n-way classes per batch. So this is what this line of code is doing. And then you have this index batch, which will store a list of lists in which one list contains a few samples belong to one batch, belong to one class. So this is what it's doing. Indices per class, and then you select the class from the class batch that you select above. And then in each slice, you select an extra k-short, like the number of samples. And then you increase the start index so that you keep moving along the list of samples you have and add them to the batches. Yes. And now we can create our data loader into with PyTorch. And for our experiments, we would use a 5-class 4-shot training setting. So each support set would have 4 examples from 5 classes, so 20 images overall. The best practice is to usually to keep the number of shot equal to the number of sample images that you would provide to the model during test time. However, this is not always easy to define in advance. So what we do here is that we would just pick 4 as an example, and then later on we can have experiments by increasing the number of shots, like the number of example per class, and then see how it's going to affect the performance. So this is just the code to initialize the data loader that we implemented before. So for simplicity, we implement the sampling of a support and query set as sampling of a support set with twice the number of examples. So So you just simply have to call the create data settings once, and then each class would have 2 times the number of example, and then you can split those example into 2, and then use one as a support set and the rest as the query set. So this is the function to split those into 2. And here is the code to just visualize some of the example created given the data sampler that we have before. So yes. So it is as expected. The support and the query set have the same 5 classes, but different number of examples. And the model will be asked to classify the 5 samples. No, wait, should be this direction. 5 samples from the query set by learning from the support set and its labels. So I guess that was all about handling the data and preparing them, get them ready to do training and evaluation. Is there any question so far? Okay, then I guess we can get into the more interesting part, which is implementing our meta-learning model. So first we define the encoder function that encode the images to be densenet. So it's just a common choice for image encoding, and of course you are free to plug and play to see if there's anyone more interesting, but it's just the one we choose for this setting, for this practical. And we define a model training function that is specific to PyTorch Lightning, which you can also take for granted. Now we will discuss the first type of meta-learning, the most simple one, which is called prototypical networks. So ProtoNest operates similarly to nearest neighbor classification. So it classified a new sample X based on some distant function between X and all the element in the support set. So as you can see here, the support set contain 3 classes, and then 1, 2, 3, 4, 5 example per class. And then once we have a new data point arrive, we would calculate the distance between this new data point and those 3 clusters that you have in the support set and see which one is the closest to. Yes, that's what I mentioned. And here, in order to calculate how close the new data points to one of the support set, which is calculate the distance between that new points and the average of all examples within that support set. And here we would call it a prototype of the class. So here, as you can see, we have 3 prototypes calculated by averaging, and then we calculate the distance between this data point and the 3 prototypes. And afterward, we take a softmax over the distances of X to all the prototypes to have a kind of a distribution, so that all values lies between 0 and 1. And here's the implementation. In this notebook, we mostly use this idea as a helper for the other methods for initialization. So we just have the implementation of it for, so it's not all the way. So this is your next to-do task, in which you're supposed to calculate the prototype of each class. So I guess it's simply just taking the mean. So for each class, you select all the samples in the support set, calculate the average, and then you have the prototype, and you would return a list of prototypes. So that's the first simple one. Any question? Okay, then we will proceed with MAMO and proto-MAMO, which is more complicated. So MAMO is short for model agnostic meta-learning, which try to adjust the standard optimization procedure to this special few-shot setting. So given a model, support and query set during training, we optimize the model for m steps on the support set and evaluate the gradients of the query loss with respect to the original model's parameters. So as you can imagine here, there would be 2 steps. First, you just do normal optimization, as with any classification problems that you learned before on the support set. But then the final loss is calculated on the query set. And then in the ideal scenario, you would backpropagate that to the original model. And we would do it on a few different support query sets, accumulate the gradients, and then we update the original model's parameters. So the whole idea here is that we're not trying to teach the model to learn how to classify these specific class, but we're teaching the model how to quickly be fine-tuned over multiple different classes. So that's the whole idea of meta-learning. So the full algorithm of MAMO is as follows. So this is the detailed explanation, but I guess you can see, you can read in more details in the original material. But on the overall level, at each training step, we sample a batch of tasks. So like a batch of multiple support and query set pairs. For each task, TI, we optimize a model on the support set by stochastic gradient descent. And this is the way we denote it. We refer to this optimization as the inner loop because it's the normal optimization process on the support set, so it's not yet meta learning. So using this new model, we calculate the gradient on the original parameters with respect to the query loss. So given the optimized model on that inner loop on the support set, we calculate the loss on the query set. And then we try to backpropagate to the original model. And as I said, these gradients are accumulated over multiple tasks and not just one, because the goal is not to learn one task. And this could be called the outer loop. So that's the overall idea. So to obtain the gradients for the initial parameters from the optimized model, we actually need second order gradients, which means the gradients of the gradient, so that we can back propagate from the query loss to the original model. However, this is quite complicated and it would probably consume more training time. So we would simplify it to be first order MAMO. So here they call it FO MAMO, where we calculate the outer loop gradient simply by calculating the gradient with respect to the new updated model, and then just add it directly to the original parameters. So it's not perfectly correct mathematical wise, but however, empirically, people find that it's worked relatively well enough, given the simplification. Yes, so that's the idea for MAMO. And proto-MAMO is simply MAMO, but with just one small modification. So a problem of MAMO is how to design the output classification layer. You can imagine that if you have different number of classes during training time and inference time, then we would just have to create a whole new output classification layer from scratch and then training them, which would be quite time consuming. And even if we have the same number of classes, then the old head simply doesn't make sense when you apply it on a different set of classes. So we would want a way to how to initialize this layer so that you can quickly fine-tune it. So one way of this is to use the prototypes, which is the first model that we have discussed, to initialize the output layer to have a strong initialization. So some people have proved that the softmax over the Euclidean distance between the new data point and the prototypes, different class prototypes, can be reformulated as a linear layer with softmax. So technically, that's how we can initialize our output layer. So the formula is that you take twice the prototypes and add the bias by the negative squared L2 norm of the prototypes. So I don't have the proof of this formula here, but you can take a look at the source, which I put at the end of this practicum. So in the following section, we will just implement first order proto-mammal for few shot classification. So is there any question on the ideas? Okay, then we can come to the implementation. So just like the pseudocode algorithm that we discussed before, at each training step, we sample multiple tasks. And then for each task, we fine-tune our current model on the support set, which is the inner loop. But we need to remember the original parameters of the model before doing this inner loop, because you would have to do inner loop multiple times, sum the gradient and add it to the original model. So what we need to do here is every time we train this inner loop, we need to make a deep copy of the model and fine tune only with the copy. So the goal of this inner fine tuning is only to get out the gradients. So the inner loop implementation is the function adapt field shot, in which you have some to-do items. After fine-tuning the model, we applied it on the query set and then calculate the first order gradients, again, with respect to the original parameters. And after calculating all gradients and summing them together in the original model, we can take the standard optimization step. So this is the piece of code. So this is your next task. Your next to-do item, in which you need to implement the inner loop function, adapt field shot. So your first to-do item is to create an inner loop model and optimizer. So as mentioned before, your first thing to do is to make a deep copy of the original model, set it to the training mode, because if there is some dropouts with the model, then you need to turn on the training mode so that the dropout actually happen, as opposed to the eval mode, in which you would not do dropout anymore. So that is one of the many things in which differs between the training and validation mode. And then you create the optimizer, the SGD optimizer, and you need to set it to zero grad. Like you need to zero out the gradient, because here you're doing multiple inner loop optimization, which are independent of each other. So it's best to not having them interfere with each other. And so at the beginning of the training inner loop, to set everything to zero grad. The next step is to create output layer weights with prototype-based initialization, as mentioned before. So as described above, so the weight of this output layer would be 2 times the prototypes, and the bias would be negative of the L2 norm. So that's what we're doing. And then we assign it to the output weight and the output bias of the model. So that's your next to-do item. Okay, yes, then I guess that's everything you need to do for the inner loop. Is there any question? Okay. Then you need to implement as well the outer loop, where your first things to do is to perform the inner loop adaptation. So here, simple, you just call the inner loop function that you have before, and then you get out the local model, the output weight and bias to initialize your model later, and the classes. Then you need to determine the loss on the query set. So the classes in the query set should be the same ones as the one in the loop. And then you calculate the loss, the prediction and the accuracy just for logging, given the function that is pre-given to you. And then during the training loop, you just do backpropagation given the query loss. And then for each set of gradients for each set of inner loops training, you would sum up the gradients and then you backpropagate on your whole original model. Then I guess that's it. So the goal here is that instead of having one single loop to iterate through all samples as before is a bit more complicated because you first optimize the inner loop, summing up all the gradients between different tasks, and then do the outer loop backpropagation. That's the main idea. Okay, so next coming to the training part. So to train PhotoMammo, we need to sample multiple support query set batches, as mentioned before. And then we would use another sampler. So the both sampler, we just try to create a single set of support and query set, but now we would have a sampler that kind of creating multiple set of support and query set for one batch. So yes, there's no to-do item, so I guess you can take this for granted. Then it's the code to create the sampler given the task sampler, and then the training. So I guess that's it for training our model. Now coming to testing, what we do is that we pick random examples in the test set as a support set and use the rest of the data set as the query set. And we need to fine tune a separate model for each support set. So as I mentioned before, the meta learning training part is not to train a model that knows already how to classify, but it's just like train a base model so that it can be fine-tuned faster afterward. So in every setting, in every testing setting, we will need to fine-tune a separate model, which can be time-consuming. And here we will test with different number of K, as in different number of examples belong to one class as a support set. Here you need to implement the inference code. So the first step is to fine-tune the model, the new model on the support set. And as you can imagine, it would be equivalent to the inner loop optimization that we defined before. So we just simply use that function. And with running the model and evaluate, again, is the same run model function that you used before. And during evaluation, note that we already take some samples from the test set to be used for fine-tuning. So we should not evaluate on these samples. So we just simply set the accuracy of this set to of these samples to 0. And then when we calculate accuracy, we should remember to exclude these samples when we divide by the total number of test samples. Yes, so that's the function for testing. I hope it's clear. Okay. So in contrast to training, it is recommended to use many more inner loop updates during testing for the same reason I mentioned before, that during training, we just want to make it adapt faster. But during testing, we actually want to teach it how to classify between different classes. So here we changed the number of inner loops update to 200 as opposed to before, which I don't remember the numbers anymore. And then we can use all the function that we implemented above to test our model with different number of different number of samples in the support set. And as you can see here, is quite intuitive. As the number of samples increase, the accuracy of the models also increase, which makes sense because the more samples the model can learn from, then I guess it's easier for the model to predict the correct classes. And if we plot the result, then here we have, so as you can see here is quite impressive that already at 8 samples or so is already obtained relatively okay performance. And doubling the amount of samples from 16 to 32, the curves start to flat out, which proves that the model was successfully being able to make use of only a few number of samples for fine-tuning in order to classify the whole new set of classes. So yes, I guess that's it. Any question, comments? Okay, if not, then I guess we're done for this practical. And thank you for coming.